Hi, good morning, good afternoon, good evening, class. This is Mr. Arocena, and on today's video, we're going to be talking about Kirchhoff's circuit rules. So this is kind of the one of the more important rules for this for circuit analysis, in combination with Ohm's law and the electric power equation. All right, so Kirchhoff had two rules. The first rule was Kirchhoff's voltage rule, which is in reality kind of just a rewording of conservation of energy. Basically, Kirchhoff noticed that if you have one path in your circuit, then all the voltage drops in that path must equal the terminal voltage of the source. So you can sort of think of it as if I have a battery, that battery needs to supply energy to everything on that path. So voltage being the amount of energy per charge, all of that energy, so all of this energy has to be given to this component, and that component. Energy delivered at each component cannot exceed the amount of energy given by the power supply. So in reality, Kirchhoff's voltage rule is really just a conservation of energy. Mathematically, you can show it as the terminal voltage is equal to the voltage at component 1 plus the voltage at component 2 plus the voltage at component 3 and so on. And this is all components on the one path. Okay, so let's go through an example of calculating this out. So here's a simple series circuit with only one path, and it's asking us to calculate what is the resistance in this unknown resistor. Okay, so Kirchhoff's voltage rule states the following. The terminal voltage of the battery must equal the voltage at each component. We have 3 components. Okay. Component 1 is a resistor, so we can use Ohm's law to calculate the voltage at component 1. We'll call this R1. At component 2, we can use Ohm's law again to calculate the voltage at component 2. I should label that I2, I1. And voltage at component 3, again using Ohm's law, we can calculate the voltage at component 3. Now, being a series, so because series circuit, we can show that the current is all the same. That should make sense because there's only one path for the electrons to travel, there's only one path for the circuit to flow, so the current must be the same in all of them, and that current will be this. So for voltage across component 1, we can calculate it as 3 amps times 3 ohms, so this is going to be 3 volts. We don't know this, but at the very least we can say that this is going to be 3 amps times R. V3 will be 3 amps times 2 ohms, which will be 6 volts. Now we have V1 and V3, so in our original equation here we can say, okay, V1 is 3 volts, V2 we can write as 3.0 amps times R, and V3 we can write as 6 volts. Terminal voltage is 24 volts, and then we just do some algebra, so we'll subtract that, so this will be 15 volts equals 3 amps times the resistance, and therefore my resistance is going to be 15, let's do this, we'll divide this by 3 amps, divide this by 3 amps, so my resistance is going to be 5 ohms. There we go. So that's how we use Kirchhoff's voltage rule to show, or to help us calculate unknown values within the circuit. Now, what do we do with multiple paths? Because with multiple paths, we have more than one current. And this is where Kirchhoff's current rule will come into play. So Kirchhoff's current rule is in a roundabout way saying that the amount of charge flowing through the circuit doesn't change. So the way it's worded is that the sum of currents leaving a junction must equal the sum of currents entering a junction. And this is really, again, like I mentioned, a conservation of charge. So a junction is basically anywhere that the current splits. So this would be an example of a junction. So let's say I have a current flowing into the junction. We'll call that I in. And then leaving the junction, I have two separate currents, I1 and I2. Now, because the amount of charge doesn't change once it hits this junction, the charge flowing through I1 and the charge flowing through I2 must equal the charge coming into it. You sort of think of it like if I'm throwing 100 electrons into this junction, 100 electrons must leave. They don't just randomly disappear. So you can rewrite this as follows. I1 plus I2, and if there's multiple paths, this just goes on continuously. And this is also true if you have sort of a situation where you've got two currents entering a junction and then leaving. So if I have I1, I2, and then here I've got I3. Again, if I've got 20 electrons flowing into here and I've got 20 electrons flowing into here, the number of electrons leaving must be the same. So I'll have the same number of electrons. So in a situation like this, you can say again, the current flowing into the junction must equal the current flowing out of the junction. And then this, in combination with Ohm's law and Kirchhoff's voltage rule, will allow us to calculate a lot of things about circuits, especially more complicated circuits. All right, let's go through an example of this. So here is a simple parallel circuit, and we're asked what is the current through each resistor. All right, so as I mentioned before, here we will have some amount of current going into this junction, and then we'll have some amount of current leaving the junction. So we'll call this I2, we'll call this one I1, and we can call this I total. Now when I analyze a circuit like this, I like to show that going through the battery, I like to call this current the total current. So the current flowing through the battery represents the total current flowing through the system once all the currents kind of meet up. And it becomes very handy because then you can say the following, where the terminal voltage or total voltage of the battery is equal to the total current of the system times the total resistance of the system. There we go. Yeah. So when you have more complicated ones, it's handy to sort of keep this in mind. Okay. And the total current is what's flowing through the battery. Anyways, when you are given a parallel circuit like this, it is handy to identify how many paths you have. I'll write down path 2 down here. So in this particular example, we have two paths. We have a path that goes from the battery through this resistor and then back to the battery. And then we have a second path which goes from the battery through the second resistor and then back to the battery. And when we analyze parallel circuits, we always analyze them one path at a time. So for example, in path 1, we can say that, okay, my terminal voltage has to equal the voltage at component 1 because of Kirchoff's voltage rule, which basically says that if my electron chooses to go through path 1, so if my electron goes through path 1, it has to give its energy to this resistor, and there's nothing else to give that energy to, so this resistor must get all of the energy. So we can say, okay, here's the voltage drop in path 1. Now we can say, okay, using Ohm's law, we can show the following. 6.0 volts is equal to the current going through that resistor times its resistance, which is 35 ohms. So we can show that the current is going to be this 6 volts divided by 35 ohms, which is 0.17 amps. Okay, so that's the current going through resistor, this 35 ohm resistor. Now in path 2, we can do the same thing. In path 2, the electrons have to travel through this component, and then they get back to the battery. So all the voltage of the battery is going to be delivered to that resistor. There's only one resistor in that path, so we can just write this down. And then we do the same calculation. 6 volts equals the current, I2, times the resistance of 22 ohms. Doing our algebra, we get the following. 6 volts divided by 22 ohms, which gives us 0.27 amps. There we go. So that's the total current going through the second resistor. Now, total current, I know the example doesn't ask us, but usually this is going to be one of the questions. So total current is just going to be the sum of these currents. So, because we have a 0.27 amp current flowing into that junction, we have a 0.17 amp current flowing into that junction, so we just add them together. 0.27 amps plus a 0.17 amps, so altogether we have a total current of 0.44 amps flowing through that circuit. So that 0.44 amps will be the current that flows through this battery. And then we can use that current to figure out the total resistance of the system, which we might as well do as sort of an aside. So total resistance would be voltage, the total voltage divided by the total current, which would be total voltage was 6 volts? Yeah, 6 volts. 6 volts divided by 0.44 amps, and that will give us a total resistance of about 13.6 ohms. Yeah. Now, one thing that you can sort of, if you're unsure whether you're doing things correctly, is to compare the current in each path. Generally speaking, if you have a lower resistance in that path, you'll have a higher current. So here, for example, we've got a 22 ohm resistance here and has a current of 0.27 amps. Here we've got a 35 ohm resistor and has a current of 0.17 amps. And that makes sense because we have higher resistance leads to lower current. Lower resistance leads to higher current. Okay. So here's some quick examples of how to calculate or how to use Kirchhoff's circuit rules. And the best thing I can remind you of is that when you are analyzing more complicated circuits, consider drawing out the path and then just analyzing paths one at a time. Alright, your assignment for today then is going to be basically more practice on this with increasing difficulties of circuit diagrams. Worksheet will be linked in the description below. If you have any questions, you guys all know how to contact me.